Welcome to this video lecture on scientific research in information systems about the introduction to information system research as a science. This particular video lecture is the third part of a series of video lectures, and in this particular video lecture we will be talking about the main scientific principles. The main reading for this video lecture is Chapter 2, Information Systems Research as a Science, from the textbook Scientific Research in Information Systems, the Beginner's Guide, the second edition, which is available from all major resellers and book publishers and available electronically via the link provided. To understand the main scientific principles, it's very useful if you look at the earlier videos around the evolution of science and how these principles came into being. Some of that will be discussed in this lecture as well. In principle, what we mean here is the intellectual and practical activity encompassing the systematic study of structural behavior of the world through observation and experiment, which is one of the commonly accepted definitions of science, which has the goal of discover laws, propose theories that explain phenomena in the world that concern us. Now, in the definition, it says physical and natural world, but so most people would say this is the real world. But of course, there could be other aspects or other realities that are not physically or existing or naturally occurring these days. For example, virtual realities or digital realities, things that happen online which do not have a direct, very tangible physical or natural counterpart in the real world. So these types of worlds, these part of the human existence, also matter to science, as do socially constructed things like families and cultures and organizations, which again are not physically existing and naturally existing, but they're socially constructed and still matter to our reality and our existence. So science is not very strict on these different types of realities. It does have different disciplines that look at these different types of realities. For example, there is this idea of a natural sciences, physics, biology, chemistry, that look at physically and naturally occurring aspects of the reality. And there are social science like sociology and anthropology and psychology that look at social elements or not physically existing yet still important aspect of reality. Information systems research as a socio-technical science also looks at digital or virtual or online types of realities that, physically speaking, only exist as electricity that flows through computing devices, but of course in the manifestation that matter to humans are still real, like this video here. Science has this goal, and it also has a set of principles, like a procedural model that govern the research process and tell us how we should, discover laws and propose theories that explain these different realities and that distinguish scientific research from other forms of research or inquiry, and which is called, very loosely called, the scientific method. So that means science here in this understanding is both a product, a contribution to the body of knowledge, which we covered in the last video, and a process, namely a way of saying that we do research, that we do things scientifically. So we have a particular way of doing research that we would call scientific research, and that would be different from other types of research, like marketing research or consultancy research or self-research or desk research and so forth. So with this distinction, we can now look at information system research as a type of science, as a particular product of science. First, it is not a natural science. It is by definition a social science, because as a socio-technical disciplines, it looks at social elements and social aspects of realities. Usually this could be, what people do, what firms do, what organizations are doing, all of these social entities. Yeah. So IS research inevitably involves people and the relationship between people, say in a team or organization. And of course, importantly, the relationship between people and a digital artifact, technology, right? That's why it's a socio-technical field. Yeah. So we study digital technology in socially in use in social settings, yeah, in businesses, at home, in our love life, in relationships, for gaming, God knows whatever else. And we also discussed in an earlier time that because of that, information systems research is a methodologically and paradigmatically open or pluralistic field because there are many aspects to this socio-technical relationship between people, amongst people, and in relation to digital technology artifacts that we can study from many different ways, quantitative ways, qualitative ways, through engineering and through empirics and so forth. So as a product, the science of information systems research is pluralistic, but it's also a social science. That is important because unlike the natural science, which are also called the exact sciences, social science are invariably error prone. A lot of phenomena and a lot of measurement and instruments that we use to study these phenomena are vague, imprecise, non-deterministic, ambiguous. We talk about things like usefulness of technology, satisfaction with technology, performance of a person or a behavior of a firm. These things are not quite the same as measuring the geospatial attributes of a naturally occurring thing, like a planet or a star that moves, you know, according to laws of gravity and so forth. These are socially constructed things. Usefulness depends on what we mean with usefulness. So in itself, it is sort of an erroneous discipline. It is can never be as exact and precise as some of the natural other exact sciences like mathematics, for example. Um, but the interesting thing about information systems as a socio-technical field that it's not only a social science, it's also a technical science, or what Herbert Simon in his Nobel Prize winning work called an artificial science. Because we're not just studying people like the sociologists and other social scientists are doing, we are also studying these digital technologies, which are man-made artifacts. They are not naturally occurring. They're physical in a way, right? That we can touch them and see them, and so we build them, right, with hardware and software and so forth. But they are artificial, not natural, right? And the sciences of artificial, where this idea is coming from, where Herbert Simon got his Nobel Prize for, or, partially at least anyway, was that he said, well, our reality, the reality of the human existence, is of course shaped by naturally occurring things, or oceans, or planet, or solar system, wind, water, temperature, and these sorts of things. It's also shaped by socially occurring things, families, nations, businesses, economies, and all these other sorts of socially constructed things, language, and so forth. But our world is also filled and shaped by architected and engineered artificial things. Yeah, airplanes, cars, bridges, walls, buildings, computing devices. So we need also to study artificially occurring things and aspects of our reality. And these are different because they're not naturally occurring, they are man-made. People had an idea, they designed it in a particular way, they made choices and so forth. So digital technologies are artificial artifacts that are human created. So invariably, information systems research is both a social and an artificial science. It involves the study of the designs used to perform tasks, fulfill goals, and functions with the artifacts. So that is very important because that distinguishes information systems research from many, many, if not all other types of scientific disciplines. Now, but science is also a process, so we can also have a look at how we do information systems research through the scientific method, right? So as a scientific process, the process of doing science, scientists have over the centuries since the scientific revolution in the Middle Ages relied on certain patterns for doing science that allow us to discriminate scientific research from other types of research and to evaluate research, to saying like this is good research, this is not so good research. This pattern for doing science relies on systematic procedures for testing to see what we think is happening is in fact really happening. So there are several of these principles, and I will discuss 5 of them. The first important one is the centrality of observation. To understand this, we need to go back and think about how we constructed and used and furthered knowledge prior to the advent of the scientific revolution. Historically, much of the science did involve experiments. You can find experiments in the back days of uh, Plato and Aristotle and ancient Greeks and in ancient Egypt and so forth. So it's not that we've never done experiments before, but science and the construction of knowledge was a theoretical, a philosophical approach. In other words, verbal written arguments, what people said would happen, were more important than actual observations made in the real world. Part of that is that much of the knowledge construction was dominated by religious leaders who had knowledgeable, books of knowledge like the Bible or other types of writings that said this is how the world is, this is how we should behave, this is what's important, the Ten Commandments and so forth. And even Aristotle and Plato and these sorts of things, they were philosophers, so they had basically all sorts of theories of why things are the way they are. We did not quite focus on what was actually going on in the real world and how any of the mechanisms that we could see. Yeah, so a typical explanation is this is how God made it. Yeah, this is how and why things are. Well, because some deity made it this way. It took a person that's called Francis Bacon or Sir Francis Bacon. He was the first to call for a systematic, a practical approach that put observations, empirical experiments, and collections of data from what was actually happening in reality as the basis for scientific progress and saying like instead of listening to what the books are saying, we should look at what we can see in the real world, what's happening, and that is the basis. We should collect that, we should assess that using reason, and importantly also we should subject that to reviews by other scientists to see if they agree with me. And this was the turning point to being science as a process being primarily, not exclusively, empirical in nature. Knowledge claims that we made about new contributions to knowledge should be grounded in measurable, tangible evidence gathered through systematic observation, not just pure theory, pure reason, pure philosophy alone. This is where science departed from philosophy, where people speculate about how and why things are, to gathering information about how what they really are. So one important implication of the centrality observation is if you are in a situation where carefully collected data about what is actually happening in reality conflicts or is inconsistent with what a book or a person says, some claim about why and how it is happening, then the observations dominate. So we can trust the facts more than we can trust the writings. In other words, even if the Bible or some other text would say, you know, this and this and this is how, I don't know, how certain animals copulate, and what we see is different, we can trust that more than what the books had said. This sounds obvious now, but only because we've had this revolution 500 years ago. 500 years ago, this was completely unheard. It was unthinkable that someone would say like we do not follow a divine script, the divine texture anymore. We do not follow what people say. We look at what really is. A second claim that sort of builds on that is a notion of that knowledge claims made by scientists need to be validated through review by other scientists. This is what has become known as the peer review, that any knowledge claim, any paper, any observation, any study, before we can make it public to distribute that knowledge, it needs to undergo this peer review where other scientists, ideally, of course, experts that know just as much or more about the topic that we're studying, assess the knowledge claim, see if we did things right, and approve of that. Only then can we say this is validated a knowledge claim. So to allow for this peer review, it means that the procedures by which we created our knowledge claim, how we did things, must be conducted and documented in a way that allows others to replicate it, to repeat the procedures in a way that allows them to get the same results. So it's not enough for me to do an experiment, find something out. I must do it and conduct it and document it in a way that others could repeat the experiments. And if they did, they should find the same type of results. Um, this sounds simple. It's actually one of the biggest concerns around science going around. So this is an example from 10 years ago, which is known the reproducibility or the replicability crisis in the social sciences, specifically psychology. This guy here that you can see here, Brian Nosek, what he did is he took the 100 most important studies about psychology, the studies of the human behavior and the human being, why we do the things we do, why we get addicted to smoke, why we come help if someone cries fire, but if they don't ask for help, and so forth. And what he did, he and his team, he replicated not quite 198 of the most important psychological studies, which have all these insights that we build our policies around, that we educate our children, and so forth, and to see if they independently, by repeating the original procedures, came to the same results and conclusions. What they found is that they could only do so in 30%. In 30%, they got somewhat different results. In another 30%, they couldn't replicate any of the results. They got some completely different results. This was important because it led to the so-called replicability crisis that we realized, oh my God, we always took this for granted. We actually never bothered to replicate. And now we realize that most of the things that we have taken for knowledge are actually maybe flawed, but certainly not uncontestable, right? So we will have to go back and see if we're really right. Um, This we see the same thing in information systems. There are replication studies, and here's just a traditional examples here, right? So this was an original adoption study that got replicated by different people, actually, in fact, showing the same results. And in fact, this replicability crisis has, in our field, led to several initiatives, such as a dedicated journal, Transactional Replication Research. When you go to that webpage, you see hundreds of replication studies that people have done to repeat the procedures of the previous studies in information systems to see if they have the same results. There was also a replication project that is kind of like Brian Nosek's work, where people took 25 of the most important studies that we had done in our field over the last 40 years and replicated them. And in fact, actually showing that many of them, or let's say many more of them, could be replicated than the studies in psychology. So it's sort of not as bad as some other disciplines. This is principle number two. Principle number three that I want to talk about is this idea of independence. So simply put, that the researcher should not be biased, should be impartial, independent, and distant in a way from whatever it is that they're researching. Yeah. So research should be impartial and freed from any subjective judgment or other bias from the researcher or research team. This is extremely important in contexts such as, say, politics, political science, where researchers, of course, have their own political views, and they're meant to free themselves from this independence and study, say, what's going on in political processes, irrespective of what they personally favor. This is one aspect of independence. The other, maybe more important aspect of independence is that the researcher should be protected from external influences that would bias the results. How that is actually being done, this protection against external biases and influences, is through a process that's called tenure, or in German Verbeamtung, which means that if a scientist has proven him or herself to be a good scientist and make good contributions to knowledge, they get an indefinite appointment that can be terminated only for cause or under extraordinary circumstances. In other words, you're very well protected in your job. Yeah. And Germany has, many would say, the strongest tenure protection for scientists. So if you're verbeamtet as a scientist in Germany, you get a pretty decent salary. You get health cover for yourself, for your kids. You get a very good pension, more than other people would get. You get rooms in the university. You get a lab if you need it. You get assistants. You get people that will work for you. You get a budget to do your research, etc. What is the idea? The idea between this type of tenure system, and there are similar ones, slightly different ones in places like the US and Australia and in some parts of Asia and so forth. The idea is that we safeguard academic freedom for those who teach and do research in higher education. By law in German, constitutional law, Article number 5, Recht auf Freiheit der Forschung und Lehre, says that scientists must be protected and must be able to do their research independent of third parties, independent of a need to, work for someone to get some money, work for someone to, provide funding for your family, and so forth. So that's why the institutions in Germany and in other places give you money, give you budget, give you people that work for you, so you can do most, if not all, of the research that you need to do without having to ask a third party. Yeah. So we have conditions for us to do any research and innovation that we think is worth doing, free from corporate pressure, budgetary pressure, or political pressure. So in Germany, you are safe to do all sorts of research on things that are even societally, politically unwanted. Yeah, and then you can easily think about certain things. If you think about abortion laws, if you think about gender identity questions, if you think about right wing, left wing, extreme political positions, and all these sorts of things. Yeah. So this is, of course, not without controversies. And one very local example from the University of Hamburg is the fact that there is a professor in economics at the University of Hamburg, Bernd Lucke, who is one of the founders of the right-wing party AfD. Yeah, so this is a German political party which is right-wing extremist. Just for context, when he and others founded this party, it was probably not quite as extreme as it is now, and he's no longer a member of that party. However, was one of the founders, and it created all sorts of pressure because of many people in Hamburg and other regions said like, "Oh my goodness, this person is very right wing. He should not be allowed to teach or do research. Why are we paying him money from?" But the university said, "Look, this person has tenure. We protect him. He is safe. We safeguard his academic freedom to teach and pursue his ideas if he believes these are worthy ideas to pursue. We will protect him." And they quite literally did this, meaning that he had a police escort. People wanted to stop his lectures and so forth, but the university always protected him. Yeah. A similar, more recent example is from Hamburg is a physicist researcher called Wiesendanger, who he's a well-known physicist, but he also became quite well-known in the media during the corona pandemic because he published a theory of the origin of the coronavirus, and he suspected it to come out of a Chinese scientific lab. Now, you may remember, or you may or may not remember this, but this obviously spurred quite a intense debate. This is a very provocative kind of thing, but he did research on this. He published a scientific paper on this theory, and the university protected him, even if several people said, "How dare you say something like that?" So irrespective of whether or not his explanation, his theory is correct, the university said, we need to protect his freedom to pursue research in an area, even if it runs counter to most people think or want to think. So this is a typical implementation of independence. And as I said, Germany is actually a pretty very good place for this. And many people would say it has the best, also sort of the most protective tenure laws of all places. There are several examples, let's say in the US, where people even though they did have tenure, got fired from the position also for political reasons or for certain societal reasons or moral reasons or other sorts of things. But independence also covers other aspects. So one of them is that you should be independent of the research that you're doing. You should be distant and neutral observer. And a famous counter of that example is actually when research on the drug LSD started. Yeah. Albert Hoffman is one of the chemists that actually sort of invented LSD, and he wanted to understand what it does to people. What he did is he self-administered LSD, and he said, "Oh, I'm a scientist. I'll, put myself in a lab. I'll take notes of, what I'm experiencing when I'm taking a hallucinogenic drug, LSD. How else are we going to find out? So he self-administered it, and he basically wrote a protocol while he was high, so to speak. And this is a quote from this. I perceived an uninterrupted stream of fantastic pictures, shapes, kaleidoscopic play of colors, and so forth. And this was just the beginning of the trip, so to speak. And he got even higher, and then, his protocols basically went out of the window. So he couldn't really rationally follow his own self-experiment anymore. And obviously, this is something that we would actually call unscientific because it violates this principle of independence. There are more examples. One more is from the tobacco industry, which is a very well documented case of research where the principle of independence has actually been violated quite substantially. There's a movie about this, Thank You for Smoking, with Aaron Eckert in the leading role, which you may want to see, which is about the tobacco industry and how it sort of tries to influence research to alter the statements they make about how good or bad smoking is for your health. So the tobacco industry is an interesting case because it has a long history of interfering with independent science. In the 50s, after the Second World War, when the first scientific results that said basically smoking is bad for your health, they simply refuted the data. In the 60s, when the scientists wouldn't stop making claims that smoking is actually bad for you, the tobacco industry hired very expensive law firms that started suing the scientists. Now, if you put yourself in the situation of the scientist and then you get a lawsuit from Marlboro or Camel or some of the other players, that can be pretty daunting. And universities at that time didn't have legal departments that would step up and defend the scientists. So all of a sudden you're in a lawsuit where a company sues you for billions of dollars for a claim that they're refuting. So this led to universities actually stocking up in legal departments and assuring getting legal protection for the scientists so they can actually even fight such a lawsuit, let alone, that you don't automatically lose it because you don't have the same bargaining power. And then a couple of decades later, what actually happened is that these types of industries, they can't refute the science anymore. They're also not just legally sort of stopping this research from being done. So they basically opted for a co-opt strategy. You will find a lot of research centers on sort of tobacco, smoking, or just air quality that are actually funded by tobacco industries. So entire institutions with buildings and salaries for people that are funded by tobacco companies. For example, there is a well-known center for indoor air research funded by Philip Morris, the tobacco company. And now you can ask, okay, how independent is the research that's being done with the funding of the tobacco industry? Yeah. There are also purposeful, deliberate violations of independence. For example, there's a particular form of doing research that's called action research that is by definition not independent because the entire point of action research is that researchers study a problem in an organization and then introduce a solution in the organization and study how effective the solution is. That's the entire point of action research. And by definition, this violates independence. You are not an independent third-party neutral observer anymore. You're a change agent. You are introducing change. The history of action research goes back to post-World War II in Britain, where researchers wanted to work with the large companies at the time to apply social science to contemporary issues and problems in the firms. And the research institutions at the time, the universities and the federal ministries for science, they said, you can't do this. This is not science because you're not independent. It's sort of consultancy or something. So what these people did is they basically created an institute of their own right, where they maintained independence because their salary wasn't coming from the firms, but they did get funding from a variety of firms, Unilever, Calico Shell, British Petroleum and others, so that they could research and introduce new management approaches, such as new technologies, women as CEOs, which wasn't a thing at the time, and so forth. This is a form of research called action research that is deliberately violating the principle of independence. In information systems, We do some action research, but we also have our own variant of that, and it's called action design research. That is a fairly or reasonably popular research method in information systems that is combining this idea of action research, introducing change, with design science research, building a new technology artifact, where we build an artifact and implement it within a concrete organization. Now, this is an established methodology. There are guidelines for it. It's accepted. You can publish these papers. People call that scientific. But just keep in mind that, strictly speaking, it is violating the principle of independence because you are building an artifact, which is fine, but you are also putting it into an organization and studying how they then use it. Yeah, so I'll give you one nice example of a paper that I actually quite like. This is a design action design research, which is a couple of people from Australia and other places that worked with a company doing wildlife monitoring, and they built a new technology, like a new software that helps them to create sort of like an analytics dashboard based on, sensors and measures in the woods where they see, I don't know, how boars run around and deers and all these sorts of things. So that's an action design research project. There's a screenshot from part of the analytics platform that they built and introduced and studied in an organization that does wildlife management, if I'm not mistaken, a government organization. The next principle I want to talk about is precision. The precision is the idea or the request to define, concept, construct, measurements, data, observations as carefully and precisely as possible so that others can use, apply, challenge these things in their own work. Precision is directly related to the notion of a scientific instrument. So when you looked at the video lecture about the body of knowledge and one of the aspects being measurement, this is related to precision and the role of scientific instruments, technologies that we use in science to measure and observe certain things. Scientific instruments are important because these are instruments or technologies that enhance and go beyond the actual human senses that we have to perceive the world. So eyes that are better than our eyes, touch that's better than our touch. Yeah. Precision instruments that go beyond what we humanly would be capable of observing. So that means we can more accurately measure the world around us than with our senses alone, or we can make things measurable that are not perceptible by the human senses, such as the surface of the moon. We cannot see the surface of the moon with our own eyes because it's too far away. We cannot see the anatomy or the cellular structure of biological beings with our own eyes because they're not precise enough. So these notions of scientific instruments, the quest to become more precise in measurements and observations, was really key to the entire beginning of the scientific revolution because this was the way that you could actually refute and disprove theories that had been held for thousands of years. Yeah, and one of the obvious examples is the refutal of the geocentric view of the world, where we have a flat Earth in the middle and the solar system and the planets revolve around the Earth. To the naked eye, this is what it looked like, and we've believed that for thousands, hundreds, if not thousands of years, that the Earth is flat. There's a horizon where we drop off. The sun rises in the east and it goes down in the west, and and the moon and the other planets that we can see, like Venus, for example, they revolve around the Earth. It was only through the invention of more precise measurement instruments, particularly the telescope by Galileo, that he could see actually they're not revolving around us. Actually, it's not even a circle, it's an ellipse. And actually, what is really happening is that the Earth and other planets are moving around the sun. That is the much better explanation that is more consistent with the observational data that I'm getting through more precise scientific instrument. And these instruments, as I said, they were really key to the beginning of the scientific revolution. When you look at this, we had the telescope, we could see better. The microscope, we could see smaller things. The barometer, we can measure air aspects like pressure better. Thermometer, we can measure more precisely temperature. The pendulum clock, we can measure more precisely time. Yeah, all of these instruments were really key to starting a scientific revolution that put the centrality of observation in the middle and allowed us to challenge theories that had stood the test of time through our own observations for thousands of years. And again, we see these types of precision instruments being continuously developed to this day. One example from information systems is a stream of research that calls itself NeuroIS, neurological measurements in information systems. What these people are doing, they are using neurological measurements like an fMRI, eye tracking, these sorts of things that take measurements, more precise measurements from what's going on in our brain, in our blood, in our pressure, in our body, and relate them to technology phenomena. Yeah. So, for example, how we get sort of used and accustomed and bored by information system security warnings like, hey, update your passport, or be careful, this is not a strong password. Over time, that our brain reacts, and our eyes and our brains react to these messages less and less because you're getting so and so bored and used to them, and so an habituation process. So again, this is a recent advance where we are getting more and more able to look into our own head. Having said that, the measurement itself is actually still very imprecise because what we can do now, which we couldn't do for thousands of years, is we can sort of highlight regions that are activated in the brain, right? And you can see this on the image here. They sort of, hey, there's something going on here. Look at that. It's a little bit more red or yellow, or, a little bit more active. That's not a very precise measurement in itself. So the quest for more precise instruments continues. The next important principle I want to talk about is the notion of falsifiability. Falsifiability has emerged as a key standard of evaluation for theories and hypotheses. Falsifiability demands that any assertion, conjecture, proposition, hypothesis, theory, any proposed explanation, in principle, can be contradicted by observation. It must be possible to prove your theory wrong. If your theory is constructed in a way that it cannot be proven wrong, it is not a scientific theory because it's not falsifiable. Yeah. So this goes back to work by Karl Popper, who wrote a book in 1930s called The Logic of Scientific Discovery. So this is not actually old even. It's not even 100 years old, this idea of falsifiability. And his key observation was this, that it's impossible to verify conclusively that any proposed explanation is always going to hold true. Simple example is Newton sat under the apple tree and the apple tree fell to the ground, and he said, hey, there's this thing going on here. Let's call it gravity. Gravity is actually the apples are not actually falling from the tree. They're being, so gravity pulls them towards the earth, which I guess most of us would believe. But it's logically impossible to prove that even though all apples have fallen from all trees always to the earth, it is possible that tomorrow's apple will shoot to the sky, thereby disproving gravity. And it's impossible right now to prove conclusively that this will never happen. So, meaning that we can never, ever verify a theory. We can never conclusively prove a theory. Verifiability is impossible, but falsifiability is possible. And the typical example through which this explains is the theories about what swans are. Swans, for hundreds of thousands of years, were theorized or explained to be sort of like goose-like creatures that can swim and fly and are white. Yeah, so one of the defining characteristics of a swan is that it's a white animal. Except that when people discovered Australia in the 18th century and sort of populated this, you have black swans in Australia. They're actually quite famous. Yeah, but that wasn't known until 200 years ago. So the existence of a single black swan, which was exactly like a swan, like any other swan, except that it had black feathers, disproved the theory that swans are white animals. Yeah, so just a single swan is enough to falsify an existing explanation. So the key point here of falsifiability is that theoretical explanation can never be proven to be correct, but they can be proven one with a single observation. So that means that For scientists, our theoretical explanation must, in principle, always be rejectable. It must be possible to execute a test that would prove a predicted explanation to turn out to be incorrect. The idea would be that we have predictive theories, theories that would predict something, testable and therefore useful. And how Popper came up with this is that he contrasted two the most famous scientists at his time, right, early 20th century, which was Sigmund Freud and Albert Einstein. And they're very different scientists. Sigmund Freud was, running psychoanalysis. He was studying patients. He was doing experiments on them to come up with his theory of, superego and Oedipus complex and these sorts of things. So he was sort of looking to be an empirical scientist. He was doing observations, experiments all the time. Einstein never did that. Einstein stayed in Munich, thought about stuff, and then proposed sort of mathematical formulas about things that should happen when time bends around, you know, dark holes and these sorts of things. And Popper asked himself, which of the two is a better scientist? And where what Freud was doing looked like science, he concluded that Einstein was the better scientist because he came up with theories that while he didn't prove them, while he didn't even empirically experimentally test them, his theories could all be tested. For example, 10 years ago, there was a very big test of a prediction about gravitational waves that Einstein made in 1914, and it took 100 years to build the measurements and precision instruments that will allow people to study gravitational pull in the vicinity of dark matter in the in space, and they were exactly as Einstein predicted them. Yeah, so his theories were predictive, they were falsifiable, it was possibly true to refute them. Whereas much of Freud's work were about sort of unmeasurable things like your superego and other types of concepts that by their own definition can't be tested, can't be measured, and hence can't be falsified. So this is the sort of the story that's behind the discovery of falsifiability and the impossibility and verifiability. And there are several examples of beliefs and explanation and theories that were eventually disproven through science. So one of them is the idea of equivocal generation. So Archimedes is the originator of that sort of when they wanted to make gold out of rocks or, in alchemy. Yeah, so the idea that you can turn something and turn it into something else. The origin of that theory is that he saw rocks at the beach. Yeah, rocks, inanimate matters, just rocks that if you studied them over the season, all of a sudden they turned grew and they grew algae and these sorts of things. So his conclusion was this equivocal generation that life can originate from rocks. And it took several hundred years or thousands of years for Pasteur and other scientists to discover, well, no, it's actually bacteria that are invisible to the human eye, but with a microscope they become discernible, and you see that the rocks weren't the cause of the algae and all this. It's actually teeny tiny bacteria that live on the rocks, and they sort of create humanly visible changes and life forms. Another example of things that was falsified is an entire discipline called phrenology, which was sort of like 100 years ago, roughly, was the discipline that studied the shape of the skull of people as the indicative of the strengths of different cognitive abilities and faculties. So they had these really weird measurement sticks that they would measure the size and shape of different parts of your head to conclude if you're a rational person, if you're smart, and so forth, and all sorts of other personality traits. That has long been disproven, but only over the last couple of years. Before that, people literally thought that the person with a weird head shape would be, would have different types of traits. This brings me to the conclusion of the main scientific principles that we introduced here and that characterize research as being scientific. Centrality of observation, replicability of procedures, independence of the research from either bias from the researcher or from outside biases, the quest for precision and better instruments, and the demand for falsifiable, not verifiable theories. This and as a summary, I want to show you this one slide where I contrasted the knowledge claims or the way we approach knowledge through science from other ways we approach knowledge. The key point here is that science is not the only knowledge domain in the world. We also have, especially in Western, in our world, in many parts of the world, we have also a religious knowledge system. Yeah, so for that also has holds some part of knowledge about the world. Yeah, for example, about Christian morals, like what we should not kill our neighbors and stuff like that. So science is not the only source and not the only knowledge domain in the human existence. There are many, many others, but they operate quite differently. So, and to make this as a very stark contrast, here I'm comparing science to fundamentalist religion, so sort of pretty hardcore religious beliefs. And they differ in many aspects. So, for example, the attitude towards truth, coined by the scientific principles that we discussed, is one of skepticism. So all knowledge, all explanations are only tentative. We can never verify them. And we always must be skeptic and test and retest and replicate them until we disprove them and move on to a better explanation. That's the scientific approach towards truth. It's only provisional, it's only liminal, it's subject to revision, it's likely wrong. It's a skeptic attitude. In religion, or in fundamentalist religion, there is this thing like an absolute eternal truth, the scripted, the sacred scripture that tells us how things are, whether it be the Ten Commandments, or sort of, other types of writings in the Bible or other types of religious texts. Doesn't have to be Christian beliefs. These are eternal and they stand the test of time, and they will always hold true. The source of authority is different, right? In science, we have the centrality of observation, so an empiricist source of facts where we tend to believe carefully collected evidence more than the explanation of whoever said that. Yeah. And the source of authority of over knowledge in fundamentalist religion typically leads with ideological or religious sort of authorities. This could be deities, it could be roles that we've invented, like the Pope, for example, or other types of religious leaders. It could be scriptures or texts. It could be all sorts of traditions that declare the authority. The uncertainty, relationship to uncertainty is very different. In science, uncertainty is quite welcome. It's the basis for inquiring or re-inquiring about things. If we're uncertain, we go back and test it again. So it's basically the basis of furthering and testing and updating knowledge. And in religion, basically, uncertainty is reduced to our uncertainty in interpreting what is absolute truth, not the actual source of the truth or the knowledge. That is basically stable and eternal, but we might interpret it wrong. So if there is uncertainty, it must be because we've done something wrong, not because some divine source of knowledge has been wrong. Methods of validation are very different, right? In science, we have this idea of experimentation and testing, falsifiability, replicability, through which we try to validate and evaluate knowledge claims. And this is again different in religion, where we have things like faith, right? We believe it because we have faith. Believe it because the leaders exercise it in front of us, and so forth. And of course, in that sense, they are both knowledge domains have different goals and react differently to changes that we see, right? So science is in the system is dynamic and self-correcting. Like through testing, falsifiability and replication, we are basically constantly updating our understanding and sort of pushing bad ideas or incompatible beliefs or old explanations. We're pushing them out of the window if they fail to meet our tests, if they fail to hold up to new data, to more precise data that we have. So it's a dynamic system that constantly updates itself. And in fundamentalist beliefs, this is typically not the case. We typically try to preserve a particular way of explanation, a particular way of living the life, and so forth. So you see, these are very different knowledge domains. This is not to say that one of them is better than the others. They're just completely different approaches to knowledge, and they do coexist, and they have coexisted for many, 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 many centuries, if not millennia. Yeah, so this is not to say that one is wrong, the other one's better, but I wanted to highlight that they're fundamentally different. If you want to learn more about the sort of principles and where they've come from, these are a couple of very nice readings, a web page about the origins of the scientific revolution, and a couple of books that I think are good because they go through the history of science and explain the nature, origin, and meaning of several of the principles that we now have come to accept. This brings me to the end of this video lecture. Thank you for listening, and thank you for watching.